Welcome back to Physics 192. I'm Gerard Blanchard. This time we're going to wrap up our discussion of optics with application of optics, and we're going to talk about such topics as optical power, combinations of lenses, and optical instruments such as a microscope or a telescope. Let's start with optical power. Optical power, which is represented by a capital letter P, is inversely proportional to focal length. So P is equal to 1 over F. And optical power is measured in units of diopter, which gets a capital D. So 1 diopter is simply 1 over a meter, or 1 meter to the minus 1. And this is the term that you'll hear if you go to your optometrist. They'll prescribe your glasses or your contact lenses in units of diopter. So the shorter the focal length of the lens, the higher the optical power is, because it has greater focusing power. It can focus the light in a shorter distance. So that's the logic behind optical power being inversely proportional to focal length. Now, if we were to take two lenses and place them in close proximity, then the optical power of the two lenses adds together. So when we have two lenses, the total optical power P is equal to P1 plus P2, or you'll probably encounter this in your laboratory as 1 over the combined focal length is equal to 1 over focal length 1 plus 1 over focal length 2. Now remember, don't add the focal lengths, however, you add the optical power. Now let's talk about that important biological optical instrument, the eye. Optically, what must happen in your eye is that the lens must focus an image of whatever object you're looking at on your retina. This means that the image distance is fixed because your eye has a certain diameter. Therefore, if the object distance changes, then the lens must change shape to keep the image distance constant for different object distances. If you are nearsighted, then that means that your lens is actually too strong to focus on objects at large distances, and we can correct that with a diverging lens, a negative power lens, to reduce the power of the lens of your eye and allow you to focus on objects at a large distance. If you're farsighted, that means that you're not able to focus on objects at small distances, and that is corrected with a converging lens or a positive power lens, which allows the light to focus from objects at shorter distances. Let me demonstrate that to you. Here you see an image of an eye looking at an object. The object actually consists of 3 lights, a red, a yellow, and a green, arranged like a traffic light. And those lights are shining from a certain distance on the eye, and the light from each of those lights diverges, goes out in all directions from those lights. This could also be a red object and a green object and a yellow object that are being shined on by another light, and they are diffusely reflecting light. So it doesn't actually have to be light sources. It could be something that is being shined on by a white light and diffusely reflecting those colors. So we'd have a red object, a yellow object, and a green object. Whatever it is, the light goes out from those 3 objects. It diverges, goes out in all directions. When it encounters the eye, the lens of the eye focuses the light onto the retina. You can see the retina. Here's the lens of the eye, and here's the retina. And the light is focused into 3 small points on the retina of the eye. The retina of the eye is all around the back of the eye right here. So the image that is formed on the retina is of 3 sharply focused points. So the image that is focused on the retina consists of 3 sharply focused points. So each of those objects is in sharp focus. For the lens strength, the lights will be in focus only at that particular object distance. If I were to take the object and move it farther away, for example, then you can see what happens. As I move the lights, as I move the object farther away, then the light is focused by the lens before the retina, so the image distance is shorter than the diameter of the eye. What happens is that the eye accommodates. The muscles of the eye will pull on the lens, they will make it flatter, they will decrease the radius of curvature of the lens, which will increase the focal length, and the light will be focused at a larger distance, like this. So now you can see once again we have the light on the retina in sharp focus. Instead of 3 blurry spots, 3 big blurry overlapping spots, we once again have 3 sharply focused spots. So that eye is now seeing those lights in sharp focus again. If I were to bring the object closer now, we'll see what happens. If the lens doesn't accommodate, then you can see what's going on at the retina. The sharply focused points of light now become an overlapping blur. The yellow gets bigger, the green gets bigger, and the red gets bigger, and they overlap, so the image of that object is once again blurry. What will happen is that the muscles of the eye will relax and allow the lens to contract and become more rounded, which will decrease the focal length of the lens, make the lens stronger. And there you can see something like that. So once again, we have 3 points of light in sharp focus on the retina of the eye. Now, every lens has its limits. Even a healthy lens can only relax so much, and there is what's called a near point, and we'll talk about that again later. That'll be important for our later discussions. For all lenses, there is a limit to the amount that it can relax. So there is a closest point at which the eye, even a healthy eye, can focus on objects. And that near point is typically about 25 centimeters or 10 inches. Okay, but a farsighted eye is one that is unable to focus on an object even at the healthy eye's near point. So let's say that this eye is unable to relax enough to focus that light at that close distance. That means that the eye is that the lens is too weak. It doesn't have enough optical power. So the way that we correct that is we add a positive power or a converging lens. And you can see right there that that lens begins to focus the light before it hits your eye's own lens, and now we once again have 3 sharply focused points of light on the retina. Actually, it looks like the red light is on the blind spot where the optical nerve is, so that eye might not be seeing that red light, but the yellow and the green are certainly in sharp focus, and the red is also in sharp focus on the blind spot right now. A person who is nearsighted, however, is a person who is unable to focus on distant objects. In this case, the muscles are not able to flatten the lens out enough so that the lens is too strong and it focuses the image before the retina. We correct that with a negative power or a diverging lens. And you see something like that, where now the image is formed on the retina. Actually, it's probably not quite the right prescription. We'll have to change that prescription. Have to make it a little bit less strong. There we go. That's a better focus. Okay. Now, that eye can focus clearly on that distant object. You can see the 3 sharply focused beams of light forming an image on the retina. Now, here's one other thing. You can also focus the light on the retina using a pinhole, like a pinhole camera. And here's how that works. I'm going to take the lens away, and you can see that the light is not focused. The eye is seeing a blurry object. I'm going to insert a pinhole, which could be just a piece of cardboard or paper in which you've punched a pinhole. And you can see how that reduces the light to 3 narrow beams which are resolved on the retina. They actually form 3 small spots on the retina. Now, the downside of that is notice how little light is getting into the eye. So even though that eye will see a sharp image through the pinhole, it will be a dim image. You're not getting as much light through that pinhole as you were getting through the lens. So notice how little light is getting into the eye through the pinhole. Those are very, very small beams of light that are hitting the retina. So we're seeing a dim image as opposed to what we would see with the lens. You can see there's a lot more light getting into the eye, so that would be a brighter image. Now, the pinhole will also work up close. We bring the light in. Okay, we're in focus, and now we're getting a blurry image. Let me make it even a little more blurry. So now here we have someone trying to read something or trying to focus on something way too close to his eye, maybe closer than his near point. And I can bring the pinhole in again, and you can see that the pinhole once again has the same effect. It resolves the image into 3 small points of light, but once again they're not as bright as with the converging lens. So that's how a pinhole camera works, or how a pinhole can let you focus on objects that would otherwise be blurry. So that's a demonstration of how the eye works. Let's return to the point that I was making about the near point. The near point, which gets a symbol N, capital N, is the minimum distance from the eye at which the eye can focus on an object. And as I said, typically N is equal to 25 centimeters. We've talked about the magnification being the image height divided by the object height, but when we start talking about optical instruments, the term magnification actually refers to something slightly different, which is the angular magnification. So how big an object or image appears depends directly on its size and inversely with its distance. And we represent that with the angle that the object takes up in our field of view. The angle theta is equal to the height of the object divided by the distance. Now what this means is that if we want to get a better view of something, if we can actually get closer to it and just decrease distance. That means that the object takes up a bigger angle in our field of view and we can see its details more clearly. Sometimes we're not able to do that, so we use an aid such as a magnifying glass, a microscope, telescope, or binoculars. And in that case, when we talk about the magnification of those instruments, angular magnification is what we mean. And angular magnification is equal to the angle that the image takes up in our eye when we use one of these aids, divided by the angle, the maximum angle that the object takes up with our unaided eye. Let's talk about a magnifying glass first. The effect of a magnifying glass is to let us bring the object closer to our eye than the near point. In the diagram here, you see an object at the near point to an unaided eye. The object has a certain height and the near point is a certain distance. So the object takes up an angle theta in the person's eye. To the right, we see an object being brought closer to the eye using a magnifying glass, and the closest that we can bring an object to the lens and still form an upright virtual image is the focal length of the lens. So the closest that the object can be brought to the eye is the focal length of the lens. So the angle in that case would be the height of the object divided by the focal length. The angular magnification would be the angle with the aided eye, which would be the height divided by the focal length, divided by the angle for the unaided eye, which would be the height divided by the near point. And when you divide those two, the height of the object cancels out, so the magnification of a magnifying lens is simply the near point of your eye divided by the focal length of the lens. So the shorter the focal length of the lens, or the more optical power the magnifying lens has, the greater the angular magnification is. Now, the near point of different people's eyes is different, but usually a typical value of 25 centimeters is used for that calculation of the angular magnification of a magnifying glass. Now let's talk about compound optics, such as a microscope or a telescope. Microscopes and telescopes work on the same principle as shown in this diagram. You are looking at an object, and it's that small pencil, and you have lens 1, which we call the objective lens in both cases. And the objective lens makes a real image of the object. So that would be the intermediate image in this diagram. And that real image is close to the second lens, lens 2, which is referred to as the eyepiece. So the objective lens makes a real image of the object and brings it closer to your eye, and lens 2 functions as a magnifying glass. So we see the object, we see the intermediate real image, which is inverted, that's formed by the lens 1 or the objective lens, and lens 2 simply magnifies the image, forming a much larger virtual image. The difference between a microscope and a telescope is that with a microscope you're looking at an object that is very close to the objective, and with a telescope you're looking at an object that's very far from the objective. So the magnification of both of these instruments depends in different ways on the focal lengths of the objective and the eyepiece. Let's take a look at microscopes first. Here you see a diagram of a microscope. You have an object, and you have the objective lens, and the objective lens is placed so that the object is just past the focal length of the objective, f sub o. So you see the objective lens, you see the focal point of the objective lens, and the object is just past that, so that a real image is formed close to the eyepiece. Then the eyepiece is brought close to the intermediate image so that the intermediate image is very close to the focal length of the eyepiece. Let me demonstrate that for you. So here we have a penny, and I have two lenses. They're both magnifying lenses. They're both converging lenses. They both have positive optical power, so you can see that they will create a virtual upright magnified image, so you can see some details better with them individually. Now I'm going to combine them in the way of a microscope. I'm going to use this lens as my objective lens, and I'm going to pull it back until we get a inverted real image somewhere up here. So there's an inverted image somewhere up here, inverted real image somewhere up here. I'm going to take my second lens and I'm going to magnify that virtual image. And there you can see that's the word liberty focused, enlarged. Let's see, get it in better focus. There we go. Let's see, take a look at the date. There we go. That's a little bit better focus. So you can see that we have the date on the penny now magnified even larger than we could with either one of them combined, either one of them individually. So this is a demonstration that you can also do on your own. If you can find two magnifying lenses, you can use them to see how a microscope functions. You would take one of the lenses as your eyepiece, and you can actually hold it very close to your eye, while you place the other lens far enough away from the object that you're looking at so that you have an inverted image, and then take the eyepiece and find the distance at which you can magnify what you're seeing through the objective. You can also make a telescope with two lenses. As you can see in this diagram, a telescope functions on the same principles as a microscope, except that in this case the object is very, very, very far away from the objective lens. That means that the objective lens focuses an intermediate image at the focal point of the objective lens, and then we use an eyepiece to magnify the intermediate image. The angular magnification of a telescope is simply the objective focal length divided by the eyepiece focal length. So to get the most magnification out of a telescope, you would want an objective lens with a long focal length and an eyepiece with a short focal length. Now, the fundamental limitation of a telescope is actually not its magnification, but more the brightness of the image that you're seeing. Brightness actually decreases with magnification because you're taking whatever light you're getting from the object that you're looking at and you're spreading it out over a larger angle. The brightness, however, increases with the diameter of the objective lens, which is why the diameter of a telescope's objective lens is the quantity that you often see quoted when referring to how strong a telescope is, as opposed to its magnification. Now, a telescope is also something that you can demonstrate to yourself with two magnifying lenses. Now, in this case, you want a stronger lens to be the eyepiece and a weaker lens to be the objective. Now, your objective can't be too weak, especially if you're just going to hold it in your hand, because the focal length of the objective has to be shorter than the length of your arm. The objective has to form a real image somewhere between the lens and your eye, so there's only so far you can get that lens away, so there's only so long you can let the focal length of the objective be. So if you have a suitable pair of lenses, then you can take the stronger lens as the eyepiece and hold it up right in front of your eye, and take the weaker lens and use that as the objective, and then you can move the objective in or out to get the image to be formed right at the focal length of the eyepiece. That's also another demonstration that you can do for yourself. So if we look at the diagram again, you see that the objective forms an image at its own focal length, f sub o, and then you bring the eyepiece in so that the focal length of the eyepiece, fe, is exactly that distance away from the intermediate image. So that combination of focal length of the objective and focal length of the eyepiece has to be shorter than your arm. And then the angular magnification of the object that you see, or the angular magnification of the image that you see, would be the focal length of the objective divided by the focal length of the eyepiece. So that wraps up optics for us. Next time, we're going to start with a new topic, electrical circuits. Until then, think physics.